back. We're going to start this morning with Lucas Mann, who will speak on 6 functors, or Pro-Étale Cohomology on V-stacks.
Thanks a lot for the invitation and for the opportunity to speak. Right, so the title says that I will talk about 6 functor formalism, but during the preparation I changed the plan slightly, so there will be 6 functor formalism, but it will only appear at the end. I will build on the great introduction that Jared gave on Monday. So I'll report on the same project, and the plan is to provide some more details on what exactly goes into these computations that he mentioned. So let me start by maybe recalling the main goal of our project. So Jared mentioned this conjecture, which he calls the bichromatic splitting conjecture, since last week. So it's the following statement: takes numbers t and n, and some prime large enough, then if I take the kt localization of the Ln localization of the sphere, and this I can compute as the kt localization, and then up to some exterior algebra. Okay. And they had some degrees, I think 2i minus 1. And so the way we approach this is...
It's probably 1 minus 2i.
1 minus 2i, sorry. Well, depends on homological or cohomological. Okay, anyway. One of the two. And so the approach that we have on proving this is using the following algebraic variant. So this is the algebraic bichromatic splitting conjecture. And this is the statement that under the same assumptions as there, if I take the continuous group cohomology of Gn on an mod u1 dot ut minus 1, that's t inverted, then this is isomorphic to the continuous group cohomology of gt times gl n minus t zp with coefficients just in fp. Okay, and let me also reintroduce the notation from last time. So that's gn, the Morava stabilizer group. So this is the automorphisms of a formal group of height n. Of height n in dimension 1.
Listen, I realize I made one slight error in this conjecture, that it could easily be fixed by drawing a bar over the FP.
Oh shit, sorry. Yeah, I guess
That was my error. Or you can change the GT to be a smaller group that doesn't have the Cal-Law part in it.
Yes, sorry, but I guess I intended to put the bar there anyway.
Great.
But thanks. Okay, and so this AN is the Lubin-Tatering, so it's ZP power series U1 dot UN minus 1. Okay, and sorry, I guess ZP graph, sorry, maybe I should just write W and P bar. Okay, And I think the way this is related to this algebraic is related to the homotopy statement is through this Morava E theory, and this ring here appears as pi 0 of that. And I guess you probably understand that better than I do anyway, so I'll focus on trying to explain how we can prove this. And, right. And so, let me maybe state what we can actually prove right now. So I will focus on the case that t is equal to n minus 1. Then the whole thing becomes a bit easier because then the thing that's written here is a field, and that simplifies then things. And now here's the theorem that we can actually prove in progress. Namely, I take the continuous group cohomology of Gn on, well, what's written there, it's just Fp bar, and then it's Laurent series in Un minus 1. And, well, unfortunately, so that's the guy that we want to understand. But unfortunately, currently, there's one more annoying subtlety, namely we'd have to take a completed perfection, and we can compute this guy, and that's what we expect. Okay.
Gn minus t, of course, is just... so this is...
Did I mess it up? No, I think it's fine, right? Okay, and the goal of my talk is to explain how we can prove this. And we have some ideas of how to get rid of this for completed perfection, but I'm not prepared to talk about this today. All right, so how do we prove this? Well, I split the proof in 4 steps, and they will involve lots of perfector geometry and so on, so I'll try to introduce all the relevant steps that appear there. And I think the first step is...
Just to be clear, so the right-hand side here is exactly the same as in the conjecture?
Yes. The only problem is that we have this completed perfection. And if you can get rid of that, I think it's also true that this algebraic version applies the non-algebraic version in this case. So once we get rid of this completion, at least in the case n is t minus 1, you get the statement.
You know the twists as well in the algebraic version.
Oh, yeah. Okay, I guess. But I guess we can handle those.
In this case again?
Yeah, in this case we can handle those. Yeah. So I guess in this case, once we get rid of this perfection, we can really prove the statement, as far as I understand. But don't pin me on this part because I can tell you everything about this statement there. Okay. So how do we prove this? Well, the first idea, and that Jared already mentioned, is we want to geometrize, we want to get both of these statements out of geometry, and then try to prove the statement using geometry. So the first step is to geometrize, and, okay, I will first try to geometrize the left-hand side because that's the complicated one, right? So, Jared already mentioned that perfectoid spaces and diamonds appear, so let me maybe give a rough definition of what they are. So, actually perfector spaces, the only things we need right now is perfector spaces and characteristic P, and they're extremely simple. So, a perfectoid Huber pair over Fp, or I guess in this case Fp bar all the time, as a Huber pair RR plus. So these are the things that Jared already introduced. So R is a topological ring whose topology is particularly nice. It's given by an adic topology on some open subring. And this R plus is some open subring of R, which you don't have to worry too much about. And then there's a condition, of course, such that, well, there's actually 2 conditions. The first one is that R is perfect. And the second one, well, I have to make sure somehow that I'm living in the rigid world, so in analytic geometry. And you can characterize this as there is a topological nilpotent unit in R. Okay? Oops. So once I have this definition, I can now define V-stacks. So we consider the category of the finite perfectoids. So this is just a spa RR plus for RR plus as before. So this is perfectoid over FP bar. And if you don't really know what the spa RR plus means, don't worry too much, because I mean these are all affine, right? So this category is the same, it's just the opposite category of these pairs. And maps between those pairs is, well, just maps of topological rings. So there's no magic going on here. You can basically ignore the spa if you don't like this topology in there. I need the spa for one reason, because I want to define a site in this. So equip this perf with the V site. And Jared already mentioned the V site. And well, he said it's somewhat close to the FPQC site, and that's true. But actually, to define this here is extremely simple and looks maybe a bit weird at first. Namely, a cover is just the finite family of jointly surjective maps. On these spas. Okay, so it's an extremely weak requirement, basically the least you would ever expect to have to require. And it turns out, and that's, I guess, due to Scholze who observed this, that that's a reasonable site to work with. And, well, it's also a very easy site to work with. It's very easy to check that something's a cover. Okay, and then with that site, I can now define V-stacks. So
when you say surjective, you mean like surjective on some set of valuation?
Right, so it's surjective. So that's the one place where I need the actual spa. Right, so Jared introduced that last time. So that's the space of valuations on R.
Is that equivalent to some obvious condition on R itself?
Well, I mean, I guess you can, similarly to how in schemes, you can characterize the point of a scheme as maps from some field into it, spec of some field into it. Here you can also characterize the points of this space as maps from a valuation ring, well, yeah, certain spaces that are very simple, basically valuation rings into this. And then I guess the requirement is that those can be lifted. But it's pretty much just a different way of saying that it's surjective on valuations. But in practice, I mean, if you have some intuition for how to work with these things, it's not so hard to check. Okay, and then the category of V-stacks is just the category of sheaves on this side. And by sheaves, I mean space valued or anima valued, whatever you prefer. So stacks in the classical language. Okay, and so I claim that Peter observed that that this is a nice topology, and one incarnation of this fact is the following result by Peter, namely the assignment where I take such an RR plus and I map it just to R. This is a sheaf. So this is a hypercomplete even V sheaf with values in D of FP bar on these perfectoid spaces. Okay, So in other words, the V cohomology of this assignment is like that. There's no higher V cohomology of this assignment, so it just descends directly. So I think the really note, O, which is now a sheaf on V stacks with values in D of V bar. So this is the extension to V stacks. Okay. So if I know that I have some sheaf on the side, I can always extend it to a sheaf on all stacks on the side, just by descent. Okay. And now a corollary of this is that we can finally geometrize the statement. So let I view now Gn, and maybe to be very precise here, I'll put an underline, but generally I don't really like to put it there. So I want to view this as a V-sheaf, this group. And how can I do this? Well, I can just map, well, I have to tell you where is standard prefactored space S, but I just map it to continuous maps from S to Gn. So I guess I lied a little bit. Here again, you need to know what this bar looks like. Okay, if you can show that that's a V-sheaf, and well, then it's not so hard to check that this cohomology there that we try to compute and this is the cohomology on the stack given by star f p bar un minus 1 perfected. I should maybe give a name to this guy. Modulo the action of Gn with coefficients in O. Okay, and now you see why we need the perfection, because once you pass to the set of V-sheaves, because I only have perfect test subjects, these V-sheaves, they cannot distinguish between this field and its non-perfected version. So that's the unfortunate problem we have here. Okay.
So you say what is the topological Newton pi in this?
It's just un, un minus 1. And it's a unit because I inverted it, right? And it's, if I take its powers, they converge to 0. Yeah. So I guess implicitly, maybe I should say this, implicitly I'm using here that this guy is perfected. Okay, and it's somehow the prototypical sample of a perfected space in characteristic P.
I have a more basic question. What is S in the definition of G?
Sorry, I wanted to do this. So this is a V stack. Sorry, I should have. Okay, so if this is a V stack, then it needs to be a functor from these guys.
So it's one of those spas.
It's one of those guys, yeah. Sorry, maybe I should have said that. So this is spa.
All right, so it's got a topology. Okay, great.
Right, yes.
One more question. So
Yeah.
other than Gn being a profinite group, is anything else used in this kind of thing?
No, and you don't even need that G is a profinite group. And this is somewhat similar to the idea of condensed mathematics, that you can model topological spaces by how certain test objects map in. And I mean, this side here is actually much bigger than the condensed side. So somehow, at least any reasonable topological space can be mapped in. And that's how you can model this continuous cohomology. Right, and this way we also, avoided any technical issues with this continuous group cohomology, which classically is only defined somewhat ad hoc. But now here it's really an element of commutative homological algebra. Yeah?
So do I understand the definition of GMR correctly, that you only look at continuous maps of the underlying topological space as
Yes.
Yes, so it doesn't really depend on the structure sheet.
No, right. And also this underlying topological space doesn't, like, because this space here is T1, You can ignore all the high evaluations that appear here, because they are just specializations, and continuous maps can't really do anything but specializations. So this is even simpler than it might look at first.
Is a perfectoid affine already determined by some L space?
No. I mean, you can take fields, like if I take any algebraic closure of this guy, for example, it's the same topological space. Any more questions? Okay. So we've translated the problem to a geometric one. Well, I mean, it doesn't really look that geometric, but at least it's a problem on the sides. And I said I should probably give this guy a better name, and I think Jared already introduced one last time. So this is LT n minus 1, and then we have a diamond on top. And the diamond just refers to the fact that I view this guy now as a V-stack. But it's representable, so it's very canonically one, right? Okay. So step 2. I've geometrized the problem, now I want to use this fact. And, well, Jared already mentioned that the core idea is that we have some different way of viewing that V-stack via some sort of two towers isomorphism. So, and I guess this question will also, I mean, this step will maybe also answer the question why we do work with perfectoids. I mean, a priori you could ask why restrict to that? Why not just take all adic spaces of characteristic P? Then we wouldn't have this problem with the perfection. But now, why do perfector spaces help? Well, here's one of the main reasons they are useful. And that's the Functors curve that you can define over them. So, given a perfector space S equals spar R plus, so this is in my category, then I can define the relative Functors curve over the space. Over S. Over S is the following adic space. So
is S meant to be equal to that, or is it?
Oh shit, sorry. Yeah, sorry. Thanks. Then, so I will call it FFS, and it's defined as follows. So I can take the Witt vectors of R plus. R plus is a perfect ring, so, right? So there's no problem in taking the Witt vectors. They get a canonical topology, and so, sorry, you can't really read here. Is it okay if I finish in this line and then, okay. So I can take the Witt vectors, that's a topological ring. I can take the adic spectrum of it, so that's some adic space. Then I can remove the locus where P is 0 and where tag-Miller lift of pi is 0. So pi will be a topological neopotent unit in R. I'll write this in a second. So I can take that whole guy and then I can mod out by the action of the Frobenius induced by the one on R plus. So here, sorry, I need one more line. So there, pi in R circ is topologically neopotent. Okay, and if you look at this, and you know some prismatic theory, prismatic cohomology, and so on, I encourage you to think of this space as somewhat similar to the prismatization of the space S. Okay, because I'm literally just taking Witt vectors, which is what you would expect for prismatization, but because I'm in this analytic situation where I always want to have topologically neopotent units, I'm removing the part where this P and this pi are 0. And that's it. Okay, so it's very similar. So we can use this Functors curve in the following way. So here's the theorem. Namely, if I take this LT n by n comma n minus 1 diamond mod Gn, so that's the space I want to compute the cohomology of. And this is isomorphic as a v-stack to a certain other stack. Namely, I'll first write it bc minus 1 over n minus 1 star modulo these other two groups. So that's g n minus 1 times cp cross. Okay, so this is the two towers isomorphism. And let me explain what this bc is. So where bc minus 1 over n minus 1. So this is, it's a v-stack, right? So again, it has to map S, a finite prefecture space somewhere, and it maps it just to the extensions, so x1, on sheaves, so over the structure sheaf on the Fontaine curve over S, from a certain sheaf O 1 over n minus 1 to the structure sheaf. Okay. So
on the other board, can you say again what's v of p square bracket pi?
Sorry, so this is, this v of something means the locus where this is 0. And this something here, this is elements in this ring, right? So it's very similar to algebraic geometry. If you take spec or something, and then you try to remove a closed subset given by the 0 locus of certain functions in that ring.
So is p pi in R plus?
No, p is in W of R plus, and this bracket pi is a way of mapping an element of R plus into W of R plus. It's with vectors. Yeah. Both of these elements lie in this ring.
I was asking the distinction between R and R plus.
Oh yes, they're both in. Yeah, I mean p is an element that comes from the vectors, and this pi is an R plus. Sorry, maybe I should have said this. So this implies being topologically nilpotent always implies that pi lies in R plus. Okay. You mean here? Well, there's a Frobenius acting on R plus, and it extends to Frobenius on W of R plus. So it's not a morphism, and a quotient by the action of that. A priori, that might be a stack, but it turns out that that's still netic space. But don't worry too much about it. Okay. Maybe I should also say, so this is not the standard notation. In periodic geometry, people tend to denote this just XS or something. I guess that's because originally when Farc and Fontaine defined this curve, they just called it X. And I think they literally called it the curve. And I guess maybe this was intentional or not, but I guess that's the best strategy of getting something named after you, right? Worked in this case. Okay. Right. So what is this guy? So this guy is a certain rank n minus 1 vector bundle on the Fontaine curve. Okay. I don't want to go too much into this periodic Langlands program or generally the Langlands program, but these kinds of things they appear a lot in this Fuchs-Schulze paper on Langlands. I would just want to sketch why you should expect the relation between those two. So what is the idea? Well, this LT n minus 1, so I take this diamond, maybe modulo this group action. Now just take tilde because I'm maybe not very precise of what I'm trying to say here. But what does this parameterize? Maybe we'll value on S. Well, roughly parameterizes, I mean, by definition, this guy parameterizes formal groups. And it's easier to work with p-divisible groups for us, which is very similar, so let's work with those. So it roughly parameterizes certain p-divisible groups over, maybe I should have said, sorry, this as a spar R plus. So these are p-divisible groups over R plus, and then there are certain conditions. So in particular, one of the conditions is that after modding out a pseudo-uniformizer, this group must become the one, the one of height n. Okay. So how does this relate to this other thing? Well, p-divisible groups by Dieudonné theory, they can also be written as finite projective W of R plus modules plus conditions. Okay, so this is Dieudonné theory. So that's a fundamental tool we have in, I don't know, number theory or arithmetic. And so once we are here, now we're already getting pretty close to the thing that we said there, right? So, well,
it's more than just conditions.
Well, I guess because I'm mod out by these things, I hope it's just conditions, but maybe there's structure. I hope that the structure gets away if I'm mod out by this GN. But,
the approximation would become equal if you just sheafify, be sheafify, is that all it is?
Maybe, yeah. We have a precise way of saying this in our document, but there's some details that I find a bit confusing, so I want to stick to this. Okay, so we have this. And so one of these conditions, as I said, is that this thing after modding out by pi is isomorphic to a specific p-divisible group, or in this case, to a specific module here. And, well, this like, if I have a module over W of R plus, then, well, at least I can view it as a vector bundle on the spar of W R plus. And part of this Dieudonné module structure, which I maybe should have said there, is that it also comes equipped with an equivariant phi action. So such a W of R plus module I can always view as a vector bundle on this FFS. Okay, so that's how I get to these vector bundles. And, well, so the statement is now, I view this as a vector bundle on the Planck-Content curve. So this is a vector bundle E on W of R plus. And maybe, sorry, on the Planck-Content curve over S, just by pullback. But if I just pull back to the Planck-Content curve, I might lose information, right? Because I got away from this zero, the locus where P or pi is 0. So I need to retain that information somehow. And, well, if you stare at it for long enough and use some paper by Gleason and Ivanov, you'll find out what that additional datum is that you need to recover the whole structure. So maybe let me make precise here what is this now. So this E is isomorphic. Well, first of all, I want this to be isomorphic to this certain vector bundle here. And that vector bundle is just the one vector bundle that's coming from the p-divisible group of height n. N minus, shit.
1 over n.
Yeah. Yeah, I want this 1 over n, sorry, yes. So this is just the one vector bundle coming from the p-divisible group of height n, viewed as a Dieudonné module. So this needs to be isomorphic to this. But then I need to consider these other conditions, and they translate to the fact that I have an extension of E as, well, a short XX sequence like this, if I didn't mess it up. Was it the other way? No, I think it's like this. Okay, so if you stare at it long enough, you see that these extra conditions induce such a short XX sequence, and you can also get back. Once you have such a short XX sequence, you can get from this vector bundle to a whole W of R plus module. So that's a general idea.
What was the star notation?
Oh yeah, sorry, I should explain the star. Right, so the star means, so this is, so you see if I take the x1 of O 1 over n minus 1 of O, then I just get any short exact sequence like this, or something I can put here. And there's one more object I can put here, obviously, namely just the direct sum of O and O(n) 1 over n minus 1. And I don't want this. Okay, but in this X group, that's just a 0 object, so I want to exclude that. So I exclude 0. Okay, and then because I have to mod out by the automorphisms that appear here, so I get a solution. Okay, so these Gn minus 1 and Zp cross, they roughly appear as the automorphism groups of these two vector bundles. Because I don't want to choose an isomorphism of them, I just want some things that are isomorphic to it.
So is this like an tall connected decomposition of a reusable group, but like as vector bundles?
Yeah, you should roughly think of this guy as the Étale part and this guy as the connected part of the, yeah, that's where it comes from at the end. We look at the conditions. Okay, and this guy is what I call this X or BC star. Okay, so the star just says I exclude 0. Okay, how does this help? Well, we've reduced our theorem now to the following statement. It looks good, right? Because on the right-hand side, we see the two groups that we want to appear. So in total, we reduce to the following statement now. Following theorem, namely, if I take the cohomology of this BC minus 1 over n minus 1 star coefficients in O, then I want that to be just FP bar. Okay, so how do we prove this? Well, now comes step 3. And, well, I tried to think of a name, but I think maybe the best fitting name is that this is the confusing part. So I want to understand the cohomology of the space. And the way we do this is we lift the computation of this cohomology to cohomology computation on a space in characteristic 0, which I think is, well, it's confusing. So, because this thing inherently lives in characteristic P, and the cohomology we're computing is also in characteristic P. So how do we do this? Well, now I want to introduce an actual prefectored space, because so far the ones I introduced are boring, they're just perfect, like perfect rings. So what Scholze actually did is he found a characteristic 0 analog of these perfect rings. So a perfectoid Huber pair over now ZP is a Huber pair RR plus such that, so there's, well, there are several conditions, and I don't want to write them all down. Let me say, well, I'll write them down, but I don't want to explain all of them. So R is complete. So complete, I guess, makes sense. I also want it to be uniform, which I don't want to say much about what this means. Then I want, again, the topological nilpotent unit. And then the last condition. Now I need an analog of this perfectness condition, right? And I want this topologically nilpotent unit to be chosen such that pi to the p divides p in R plus. And then I have a Frobenius map from R plus mod pi to R plus mod pi to the p. And I want this to be surjective. Okay, so this roughly says that I can take p's roots up to some error, and I can make this error as small as I want, but I can't literally take p's roots. That's the intuition behind this perfector space. And maybe let me make one remark. Very important construction of these is there is a tilting construction. Which goes from perfector spaces over ZP to the ones we had before, over FP. Okay, and it sends such a guy S to its tilt, which I denote S flat. For time reasons, I don't want to go into the definition of this, so I'll just give an example of both perfected ring and the tilt. So you can take, for example, well, okay, first of all, CP is perfected. Okay, so that's the completed algebraic closure of QP. And, well, this has a tilt. And, well, this is usually denoted just that. But I guess it's also the completed algebraic closure of the Laurent series field. And maybe 1 over Eichmann.
Well, you don't need that if you're saying algebraic closure.
Okay, right. Sorry. I keep getting anxious talking about this field. Maybe another example of what you should think of. So if I want to take a ring over it, say I join some variable t, that thing is not perfected because there's no roots of t, right? But if I add all the p to the nth roots of t, then that thing is perfected. Okay, and here I said there's always an R plus, but the perfectedness doesn't really depend on the R plus, so I'll just focus on the ring R. So this is perfected. And this has tilt. Well, I tilt the field, and then the rest is just the same. Okay. And the spa of this is usually called the perfected unitus. Well, it's not, this one, yeah, I think this is the perfection, but here it's not a perfection. I mean, it doesn't really make sense to talk of perfection characteristic 0. So I guess
it's a covalent polynomial.
Yes, and then you complete. But yeah. Okay. And then there's one theorem by Peter. Namely, for perfected S, we have a functor going from perfected spaces over S to perfected spaces over its tilt. Okay, so that functor sends some t just to its tilt. And this is an equivalence. And this has vast applications. So for example, you can restrict to the subcategory where these spaces here are Étale, then you can check that they are étale here, and this induces an equivalence of the étale sides of S and S tilde. And so the Gadol groups of S and S tilde are the same. So that's one example application of this. I think this is why they are so successful. Okay. And now, with that observation, I can make the following definition. Namely, if I have a prefactored space, over ZP, and I have any rigid space over it, or even adic space. So for X, an adic space over this space, we let X diamond, so this is now V stack, okay, and it is the following V stack. It sends S, which is a prefactored space and characteristic P, sorry, I shouldn't call it S, T, and I'll assume that this lives over S flat, and it sends it to T sharp X, and I should have said that this is the equivalence, and I'll denote the inverse by sharp. So this is now V stack over S flat. So this is how you map characteristic 0 stuff into characteristic P stuff. I want to give one example. So what if S is just spa CP flat? Sorry, spa CP. Okay, if I don't put a second ring here, if I omit the plus ring, it's the canonical one that what can choose. So in this case, it would be OCP. So don't be confused by that. And then if I take X to be the torus, so just spa CP T plus minus. Okay. So what is the diamond of this? Then X diamond. Well, in order to compute it, I need to cover this by prefactored spaces, right, because I'm mapping from those. There's a canonical prefactored space that covers this, namely the one where I just add all the p to the nth roots of the coordinate t. And, well, this happens to be a torsor under the group ZP, and so you can write this as, well, spa CP flat t plus minus 1 over e to the infinity modulo the group that is the torsor over, so sorry, that's just CP. Okay. And now how do we use all of that? Well, there's a proposition now that allows us to express this BC space in a certain way. And then now for simplicity, I will use n equals 2. And then, well, the first claim that we make is, so I want to compute now BC minus 1 star, the cohomology of this guy, right? The first claim that we make is that this is the same as the cohomology of BC minus 1 star times star CP flat modulo phi. So you should think of, if I mod out by phi on CP flat, then the cohomology should just be FP. So it shouldn't really contribute. But there's something to prove here, but maybe not so hard to believe that this statement is true. So we reduce to computing this cohomology. And how does that help? Well, sorry. Keep writing here. So n is BC minus 1 star times spa CP flat mod phi. Well, this turns, the mod phi just tells me that I have to take phi invariance at the end, so it's enough to try to understand this guy. Well, in this guy, Well, this BC-1, this was defined as some vector space. And it turns out once I've base changed to this field, I can tell you exactly what that vector space is. So what this X group is. One can just compute it. And, well, the points on CP as a vector space, this guy is just CP modulo QP. And this translates into the fact that as a space, this guy is just A1 over CP flat diamond, modulo QP. But I put a star here, right? So I have to remove 0. But now if you look at this, well, this is just the Drinfeld upper half space diamond modulo QP. So I guess this is QP underlined the same way as I underlined it before. Okay. Recall that this H1, this was P1 without P1 of QP. And now what I get is A1 without A1 of QP, but that's the same. So QP acts on this by translation, and I just mod out the section as a stack. So what happened? So maybe I should recall this H1 CP was defined as P1 CP without P1 of QP. Okay? So in total, we see that the cohomology that we're trying to compute is the same as the QP invariance of the cohomology, as the phi invariance of the QP invariance of the cohomology of this Drinfeld space. So at the end, we reduce to computing the cohomology of the Drinfeld space and then try to understand the cohomology under simple groups acting on it. So we reduce to computing the cohomology Drinfeld space. And, well, you might notice that's very similar to what the original project that Jared and collaborators did, except there's a fundamental difference here, because when I write O here, this is a characteristic P sheaf, because this thing lives in characteristic P. Sorry, I should put a diamond. So it's very different from what they did. And the cohomology that you get out of this is also very different than what you would get if you did it in characteristic P, characteristic 0. Okay, so I might want to maybe add a little O flat here, just to be sure that this guy lives in characteristic P. It's not the structure sheaf in this case. There's really this O that's coming from the V stacks. Well, and now last part, the problem of 6 functors.
So this is not, of course, a pure quality horizontal, it's like a pure identification.
What is one inequality?
I mean, it's an identification on the theorem below.
So this is not a.
No.
This one?
The previous one.
Which one?
I just don't understand. When you say BC minus 1 star times R is equal to A1.
One line down, that one.
I mean, there's a canonical isomorphism here.
This is objects of different categories, right?
No, they're both V stacks. I can take the product in V stack. I mean, these are V stacks. I can take their product.
Yeah.
Then since I put a diamond here, it is a V stack. It now lives in characteristic P. And I call this the confusing part for a reason.
Sorry, my bad.
It is confusing, I agree. I've been working with this for years now, and I guess now it's okay, but like at the beginning, it's a really confusing thing that's happening here. I guess you can call it the Scholzen magic if you want. Yeah, I guess that's one of the reasons why these prefecture spaces are so powerful, because they allow you to make these kinds of computations. Okay, so we want to compute this cohomology of this space, right? And in the literature, there exists computations of this cohomology. for other sheaves here. So one sheaf they computed for is FP. They can also compute it for O plus mod P, but this, or maybe even O plus by taking the limit. This isn't characteristic 0 though. You could also, if you know what is O for O plus mod pi, which I guess you can get from the literature, you can take the limit over O plus mod pi to the n. You can compute the cohomology of this sheaf for O plus. But now you're stuck, because you can't, so the O plus is, well, it's a sheaf where you send star R plus to R plus. And on an affinoid, R is just R plus and you invert the unit, the pi. But this guy is not a affinoid, and here it's just not true. There's no way you can get the cohomology for O flat or for O from the one of O plus. So some new idea is required. And I think in their project they had a similar issue where this thing lived in characteristic 0. And so we had to solve this issue somehow here. And well, it turns out, okay, I mean, one way to try to compute this is you cover this guy by disks. You know what the cohomology of disk is, and then you take a limit over the cohomologies on these disks. We tried this, doesn't work. So we need a different approach. And well, the idea is to use a six-functor formalism. So here's maybe, let me first introduce the six-functor formalism and then say how it helps. So this is due to me and collaborators, Johannes Sanchez and Arthur César Lebas. And it says the following: there is a six-functor formalism sending a B stack X to a certain category which we call D solid hat or X on V stacks such that well, it satisfies V descent and so once I know it satisfies V descent, in order to understand what this category is, it's enough to say what it is on an affinoid perfectoid. So if I have an affinoid perfectoid RR plus, this D solid LX is the D solid hat of A. So this is, well, it's solid A modules, so it's some condensed stuff by Peter and Destin Clausen. And you should think of this as something like complete topological A modules.
It's kind of a solid and complete vector, right? Presentation's interesting.
You mean this little hat here? Or? Yeah, ignore that maybe. This little hat doesn't change much. Like in the situation that we're in, this hat does nothing. We only need this if you want to work with very big spaces, and then we need to make a slight modification. But don't worry too much about it. Okay. How does such a six-functor formalism help? Well, now we can make, I make one more observation, namely moreover, if f from y to x is a smooth map of adic spaces over CP, say, then
Another question: what is the relation between A and R?
A is R. Sorry. Thanks. Then this map of diamonds is cohomologically smooth. In the six-functor formalism. And I can compute the dualizing complex, and it is just, of pure dimension D. I need to assume that my map is smooth of pure dimension D, and then it's just the structure sheaf on Y shifted by 2D, and then there's some tight twist, but it doesn't matter too much. So how does all of this help? Okay, I have 20 seconds left.
You mean upper streak is this tensor F
Upper, yeah, I guess.
Or you
Sorry,
can say
I guess I meant this.
Yeah.
Okay. So how does this help to compute this cohomology? Well, now if I want to compute the cohomology of this H1 diamond, well, By punctuality that I have now, this is the same as the cohomology with complex support of this guy. I take the dual and I shift by 2 because the Dirichlet space is smooth of dimension 1. Okay, I'm running out of time, but so how do I compute this? Well, I compute this using excision for, well, I have P1, CP. I have an open, namely the H1, and I have a complementary closed, which is P1 of QP. And an excision tells me that the cohomology with complex support of this guy is roughly equal to the cohomology of these, but these are both very simple, so I can just compute it. And once you observe this, well, there are similar six-functor formalisms for O plasma P and FP and blah, blah, blah. And if you observe, once you observe this, you notice that all of these computations in the literature, they can be done in the same way. So, right. Sorry, there's an O here. Okay, sorry for being slightly over time. That's all I wanted to say.
Questions?
Sorry to bring you back to this proposition, but where did this isomorphism come from?
This one here?
Yeah.
Well, I mean, one way to check this is by explicit computation, because this isomorphism, you can check, I mean, we know that this BC minus 1 star is isomorphic to the Lubin-Tate space modulo Gn. If you want to check this isomorphism, you can check before quotienting out by Gn. But then the thing that's written here is just, well, spa of some Laurent series field. And you can explicitly compute this product. It's a certain disk, perfected disk. Well, and then you can, by hand, check that this is isomorphic. I'm not sure if we've checked this in all detail, but
we're working on it.
We're working on it.
That isomorphism was, I should say, inspired by the paper of Hartle and Pink, which invented the characteristic P analog of Fargan-Fontaine before Fargan-Fontaine.
All right. There's also a version of the characteristic P Fargan-Fontaine curve, and it is pretty much just the thing that appears here. I guess that's how this relates.
Questions? Yes.
Is there a twist by 1 on the complex?
Yes, I ignore. I mean, the twist is a twist by the Galois group of QP. But since I'm working with CP, I guess if I want to be precise, because at the end I want to compute certain cohomologies of groups acting on this, I should maybe keep track of it. But for now, it's not so.
And just for any smooth map, the Weisel shift is just as we see before.
Yeah, it behaves a lot like Étale cohomology, which might be weird, but well, that's how it is. I mean, you should not confuse this six-functor formalism with any coherent six-functor formalism. Even though I'm working with something that looks like coherent sheaves, it's not really, right? Because these things are defined locally on the Pro-Étale side, and that's very different from coherent sheaves that are defined locally in the open or Étale side. It turns out there's a big difference, and the difference is something that's called maybe Simpson correspondence. Like there's lots of research in that direction, but these behave very differently.
Alrighty, let's thank our speakers.